At this point, we've seen least squares estimation. We have seen how you can formulate the model fitting to data where the underlying model is linear in the unknown using this quadratic error function that specifies a very specific objective function, the sum of the squares of all of the vertical distances. And when we formulate the model fitting problem that way, we ended up with this very nice, clean, closed-form analytic solution that allows us to find the minimum. Now, a natural question that you may want to ask yourself when you're doing this type of least squares estimation, which, by the way, regression is another word for, is how good is the model? How good did the model explain the data? So here, for example, you can see that the data is reasonably well explained by a line, whereas here, it's not quite as good. Now, you can certainly assess that qualitatively by looking at the data, but it'd be nice if we can quantify that. And the standard way to do that is with what is called the coefficient of determination, or the R squared, or the R value. And you've probably heard about that, and I'm going to go ahead and just define it for you so that you can calculate it yourself. I'm going to define two things. Big T is a scalar value, and it is the sum from I equals 1 to n data points, of course, of y sub I, the y coordinate of each of the values that you see here, minus mu, where mu is just the average y value of all of the data. So I take that difference, I square, I sum everything up, and I call that t. Now, I compute another value, big R, also a scalar value. It is the sum, again, I equals 1 to n, of each of the yi values minus yi hat, where yi hat is where would that y value be if it lived on the line that you just estimated. Ah, that looks really familiar. What is this? This is the quadratic error function. yi hat is where is that point when it lies on the line. So what I'm asking here is what is the sum of all those vertical distances, all those deltas that we've been computing. So I have these two scalar values, and the R square coefficient of determination is 1 minus R over T. So take that value, divide by that value, take the ratio, 1 minus that, and that gives you the R squared value. And the interpretation of R squared is actually very nice and intuitive. For example, if I get an R squared value of 0.49, that means that 49% of the variability between x and y, your data, can be explained by the underlying model, in this case, a line. Is that good? Is it bad? Depends on the problem. I can't say either way. But I can tell you if you have an R squared of 0, it's bad. Your model explains nothing. And if R squared is 1, you are home because you've explained everything. So high values of R squared mean you've explained a lot of the variability in your data. Low values mean you have not. And what is good and what is bad depends on the problem, it depends on the domain, it depends on a number of different factors. But here is the way that you can assess the efficacy or the power of your underlying model. Okay, that's it for this short segment. When we come back, we are going to close off the class with one last concept, which is weighted least squares, which is a slight variant on least squares. It's nice because it's going to allow us to extend our toolkit to have one more estimation technique, and we're going to, as the name suggests, remind ourselves again how all of least squares work, so it'll be a good reminder for everything that we've been doing in this section. All right, we'll see you in a few minutes.